Hi everyone, in this session we will discuss digital design using Verilog HDL. So let's begin. These are the contents of this session. First, I will describe what is an hardware description language and what are the different types of hardware description language that are available. And then I will describe what is the design methodology in Verilog HDL. Then we will see the basic concepts of Verilog and its data types. Then some of the system task functions such as dot monitor, $monitor, and $display. We'll see what are its uses here in this session, and then we will see what is Verilog module and what are the different types of ports that are available in Verilog. And finally, we will revisit all these concepts that we have learned in this session by doing practice in Vivado tool. So let's begin. So before actually knowing what is a hardware description language, you need to know its need. Why do we require a hardware description language? In previous sessions, we have learned digital circuit design, right, using logic gates. In order to verify the circuit design or in order to build any new circuit that you want, you need a circuit simulator in which you can call these digital logic blocks like AND gate, NAND gate, and all these gates, and then you can describe your own function. Let's say if I want a functionality of f is equal to a dot b whole bar plus c. For this, I will require one NAND gate and one OR gate. So I will call the NAND gate that is available in the simulator and I will call an OR gate that is available, and then I will give the appropriate signals by connecting like this. Then I will achieve my desired functionality. So by applying the signals here, you can see the output here. This is very easy by doing in circuit simulation. But what if the circuit design or functionality that you want is very complex thing where you will require thousands or even millions of gates to implement? So in that case, practically putting these logic gates manually is a very tedious job and an impossible task, and it will require a lot of time. So in that case, you will require a language where you can define the functionality, and that language will convert that functionality or that language using in that language and a tool. If you can convert that functionality into logic gates, then it will be very helpful, right? So let's take an example. If you want to design a memory, in this particular case, let's say if you want to design an SRAM memory, don't worry what is an SRAM memory. I'm just giving a brief idea. In future slides, in future sessions, we'll describe how to design an SRAM memory also. So as of now, just think I'm designing a memory where I want to store 128 words with 8-bit each word. So for this, the memory will look like this. It has 128 different words starting from 0, 1 to 127, and each word is having 8 bits, 0th bit, first bit, so on up to 7th bit. In order to design this memory, I will require a row decoder, because if I want to access any one row of this memory, I have to turn on this row and call the data that is present in that row. So for this, we will require a circuit called row decoder. Since there are 128 words, so I will require a 128-bit row decoder. In order to get 128-bit, how many inputs are required? It is just log to the base 2 of 128, which is 7. So I will do a 7 is to 128-bit row decoder. So to design this row decoder, how many gates are required? So what is the functionality of decoder? The decoder, let's say I am doing a decoder of 2 is to 4, where 2 inputs are there and 4 outputs I will require. The 2 inputs, let's say A and B, then 4 possible combination outputs are A bar, A bar B, and A, B bar, and AB, right? So to get the functionality of this decoder, what I will require? I will require simple logic gates like this. So I will require just 4 AND gates. These are my A and B. One is true input and one is complement input. Again B and its complement. Now first output I want A bar, B bar, right? So I'm connecting A bar and B bar. And second output I want A bar, B. So I'm connecting A bar and B. Now I want A, B bar, A, B bar. So I'm connecting A and B bar. Fourth output is A and B. So I'm connecting A and B. So doing this manually, it took me around 2 minutes, right? So let's imagine you want to design a decoder of size 8 is to 256. It will require how many AND gates? It will require around 256 AND gates, and each AND gate input is 8 bit, right? To do this manually, it is a very tedious job and very complex job. If you miss any single connection, your entire functionality will be corrupted. So the engineers at that time required a language where they can define the functionality of this block, and by using some tool they want to convert this language into the circuit. So that language is hardware description language, where you want to describe your hardware or circuit in a language. This is the need of hardware description language. Once the hardware description language is ready, the hardware description language, initially they used a register transfer level hardware description language, in which they will describe their hardware or circuit in the level of register transfer. I will explain what is this. But once they describe the hardware, they will require a tool called logic synthesis. What does this tool will do? It will convert the hardware description language that is described in register transfer level into logic gates. This is what we require, right? Once you got the logic gates, you know how to simulate. You just need to give the inputs and check the outputs. So this is the need of hardware description language. When it started emerging in 1983 at Gateway Design Automation, where they collaborated with DARPA, a research institute in America, where they discovered this hardware description language. So the main purpose of this hardware description language is to describe your hardware in their functionality and in their data flow, instead of doing it directly at logic gate level, which is very tedious job, right? So once the hardware description language is available, the engineer starts designing their complex circuits, and they verify and they even and they verify the circuits, and they even design very complex circuits like microprocessors or memories using these hardware description languages. So let's see the typical design flow of this HDL using HDL. So first, you will require design specifications. Once the design specifications are ready, you start describing the hardware or circuit in a behavioral model. Behavioral model means you just describe what is the output you require. In this case, let's say it is a row decoder. You will describe, okay, I need an output of one of the among these word lines should turn on. That is the behavior description. You are describing the behavior of your hardware. Once the hardware behavior you know, you start writing the hardware description, in which you will write that I require a circuit which will convert these inputs into outputs. In this case, the hardware RTL is like this. You want to get the output O1 is equal to end of input A and B, right? A bar and B bar, because O1 is A bar, B bar. We see in the previous slide. So output O2 is equal to end of A bar B, and output O3 is equal to end of A B bar, and output O4 is equal to end of A and B. See, very simply I am writing the description of my hardware. I don't need to call the AND gate and connect them to A and B or A bar and B bar. I'm just writing it in very simple English language like this. I want output O1 should be a function of end of A bar and B bar. That simple it is. And once the hardware description language is described in RTL, you will do the functionality verification of your design and testing. Once you do the testing and you are confident that your design is working, then you will you will give this RTL code to a tool called logic synthesis, where this logic synthesis tool will convert your RTL language into gate level netlist. What is gate level netlist? The gate level netlist is the netlist which is described in terms of gates. Here it is a simple English language, right? O1 is equal to AND. But here this AND is converted into an AND gate because the tool knows you have written AND, so it will use AND gate. If you wrote NAND, it will convert into NAND gate. Right? That is the purpose of logic synthesis tool. There are a lot of logic synthesis tools that are available, like Synopsys DC compiler, or even Xilinx Vivado will convert your RTL to logic synthesis. Once you got the gate level netlist, again you will do your logic verification, whether my same logic is getting applied here or not. Maybe the AND gate is corrupted, or maybe you are using a different kind of AND gate. So you need to again verify your design and test the design, and once you are confident that the design is giving same functionality, then you will move to this step called floor planning and place and route. In this step, what you will do, instead of drawing the schematics, you will draw the layouts. Layout means the physical definition of the AND gate, right? I will explain this how to design the AND gates using actual MOSFETs like NMOS and PMOS in switch level modeling. That is an advanced topic. So I'm just giving a brief idea here how to design NMOS and how to draw the layouts. I mean, basics of these things I will explain there. But right now, just consider after the logic verification step, you will do the floor planning, placement, and routing. Once you do that, you will get the physical layout of your design. Once you get the physical layout where the metal information is available, you again do the simulation and check whether the layout of this design is actually working as you required or not. Once you do that, you will do the implementation. In the implementation step, the tool will convert this already existing physical design into a board specific or ASIC specific. In this case, in the FPGA case, it will convert into board specific implementation. Once the implementation is done, you can verify the output on an FPGA using Xilinx Vivado tool. This is the typical design flow. So we have learned what is the need of hardware description language, but what is the importance and what are the different types of hardware description language? See, the first importance is it is converting your complex circuit into a simple English language, right? And the second importance is you don't need to specify what kind of technology that this AND gate is implemented, because you are writing it directly O1 is equal to end of A comma B, right? Here you are not specifying whether the AND gate is implemented in 7 nanometer technology node or 48 nanometer technology node or 40 nanometer technology node or 180 nanometer technology node or 65 nanometer technology. You are not describing the technology node. So it is independent of technology node as well as it is independent of fabrication lab also. You are not using the AND gate of any particular fabrication because you are simply writing AND gate, and the tool itself will convert into whatever technology or whatever fabrication lab you want, right? That is the second importance of HDL, where you are not choosing any particular fabrication or you are not depending on any particular technology. Once you wrote the hardware description language, it can be converted to any technology node and any fabrication lab that is available. That is the second importance. And third importance is you can do the functionality verification after writing the HDL code, right? Once you wrote the HDL code, you don't need to do the implementation. You just do the functionality verification itself. As I showed in previous slide, once the RTL code is available, you do the functionality verification, right? Here itself, you do the functionality verification, and here itself, you can do. optimization, whatever the optimization you require. You don't need to do all the steps and then you feel okay, maybe I could have optimized my design. You can do the functional verification once you wrote the hardware description language like RTL language, right? So that is one of the importance of RTL. In the case of ASIC design or in the case of circuit design, you don't have this feature because you need to connect the circuit first, and then after connecting the entire circuit, you have to verify whether the circuit is working properly or not. But in the case of RTL, you just write the code and then simply tweak the inputs so that you can optimize in the beginning stage of the design itself. And the last importance is, since it is written in simple English, you can write comments as well. You can specify different modules, you can specify different instances where it is very easy to debug. But in the case of circuit, let's say you have connected thousands of AND gates or NAND gates with wires and all. So you cannot visualize that thing. But in the case of language, what you can do is you can visualize. You can simply put what are modules you want in one place, what are the instances of those modules in other place, and you can comment them. Okay, this module is doing this thing, and this module is doing this thing, and you can optimize them based on the comments. Okay, in later stage, I want to optimize this module, so directly I will go to this module. But in the case of circuit, you cannot visualize where which is happening what. I mean, what circuit is doing it is what, because it is entirely mixed up. So in this case, since it is a language, you can describe wherever you want and then you can directly go to that step and simply modify them based on your requirement. So that is the importance of HDL. And what are the different types of HDLs that are available? There are basically three types of HDLs. One is Verilog, and second one is VHDL, and third one is system Verilog. In this course, we are choosing Verilog because, as I explained, Verilog is very similar to C language, and the syntax of Verilog is very simple compared to these two, and it will do all the tasks that can be doable in these two. So in the future slides, I will explain what is the purpose of Verilog and how to use the Verilog to design digital logic circuits. Okay. Let's see what are the different design methodologies that are available in Verilog HDL. There are basically two types of design methodologies. One is top-down design and one is bottom-up design. Let's say you want to design any circuit, right? So to build this circuit or hardware, you can start by describing the top modules of this circuit, and then you can go inside and describe what is that module is made up of, right? This is called top to bottom approach. In the case of bottom to up, you will start describing the bottom module and then build the top module based on the bottom modules. So let's take an example. Let's take an example of ripple carry counter. A ripple carry counter is implemented by using a 4 T flip-flops, right? And again, this complete circuit is a ripple carry counter. Again, this T flip-flop is implemented using a D flip-flop and an inverter, right? This is input. So the T flip-flop is designed using a D flip-flop and an inverter. So in top-down approach, how do I design a ripple carry counter? Let's say my functionality I want is a counter. So then I will use a T flip-flop, 4 T flip-flops, and connect them like this to get the functionality of ripple carry counter. Once I get the functionality of ripple carry counter using T flip-flops, I need to define what is a T flip-flop is and what is an inverter is, right? So in this way, you will flow like this in top-down approach. But in bottom-up approach, you design your own inverter and then you design your own D flip-flop and use these both to get the top T flip-flop, and then use 4 different T flip-flops to get the ripple carry counter. The flow is like this. This is bottom-to-up approach. So why do we have two different approaches? Why can't we do only top to down approach? Because it is very simple, right? You know the functionality you want, and then you know what are the different circuits you require to get that functionality, and then you know what are the different sub blocks that are required to get this functionality, right? But if you do only top-down approach, let's say you want to optimize this inverter itself with different kind of W's and L's. I mean different kind of strengths. I will explain what is the strengths maybe in advanced topics. But let's imagine one of the inverter you want, let's say inverter 2, 3, 4. The inverter 2 you want is a low power inverter, or inverter 3 you want a high speed inverter. There are different kinds of inverter you can design where it will consume very low power, or where an inverter can operate very high speed, like this. So in this case, in bottom up approach, you have a control over the very bottom are leaf cells. Once you have control over this, you can define, okay, I want a very high speed inverter for this particular T flip-flop case. There, you will require a bottom up approach, right? First of all, you will design your own high speed inverter using MOSFETs, and then you will design your own high speed D flip-flops using MOSFETs, and then using these two, you will design your T flip-flop, right? Once your T flip-flop is ready, again you start doing your top to bottom approach as earlier. Do the ripple carry adder using your own top T flip-flop where the design is high speed design. This is where we call mixed mode design, where you utilize both top down approach and bottom up approach. This mixed mode design is basically used in complex systems like microprocessors or designing memories and these kind of things. So we understand what is the design methodologies that are available in Verilog. But how do we relate that to Verilog, right? So the Verilog provides a concept called module, where each module has its own definition. In this case, the D flip-flop will be a module, or T flip-flop will be a module, or even ripple carry can be a module. So once you define your own module, let's say module inverter, my inverter, and module T flip-flop, and module T flip-flop. Once you have your own modules, you can combine them to get the functionality. Let's say your top module is module, you want a functionality of module ripple carry counter. Then you call these modules here and then implement your functionality. You require 4 T flip-flops, so I am calling 4 modules, and then you will require your own functionality. So that is how you use the concept of modules to get the relation of hierarchical methodology. Okay. In Verilog, there are 4 levels of abstractions that are available. What are the 4 levels of abstractions? Abstraction means at what level you are defining your circuit, right? I mean, whether you are defining in gate level or switch level, switch means NMOS and PMOSs. So there are 4 different modules, 4 different abstraction levels that are available. One, behavioral, or you can say algorithm level, and second one is gate level, and third one is data flow level, and fourth one is switch level. So in this in this 4, which one will be the most lowest level of abstraction? The switch level, because you are defining the entire big circuit like a decoder or a memory system in just a MOSFETs level, either PMOS or NMOS. Here you have control over the design, but this level is very difficult to write, right? To design a decoder, you will require so many gates, and to design each gate, you will require so many MOSFETs. So writing this switch level is very complex, but you have control over your complete circuit. The second least level of abstraction is gate level. This is first least level, and this is second least level. In gate level, instead of defining the circuit in switches, you are defining the circuit in logic gates, which is very uh, simpler compared to the switch level case. And the third level is data flow level. The data flow level, what you are doing is you are directly defining how the data is flowing. Let's say I want data output is equal to in 1 and in 2, right? Out 1 is equal to in 1 and in 2. So I'm directly defining okay, I want my output is end of in one and two. This is called data flow modeling. And the fourth one is, which is highest level of abstraction, is algorithmic level or behavioral level. You are directly defining the algorithms like I want if this happens or case or switch like this. You can use for loops. I mean for this to this like this. You are using the functionality of C language in this algorithmic level abstraction. So this algorithmic level is very user friendly and it can design very complex circuits very simply because you are directly writing the algorithm that you require. I want a if condition or I want a for loop of this many things. So it is very easy and very simple. But the switch level is very complex, but you have more control here. In here, you don't have that much control because you don't know what kind of MOSFET that is going to be used, right? So these are the four level of abstractions that are available in Verilog. We'll see each one of them detailed in coming sessions, and we will give the examples of each one of them, and we'll see the advantage of each one of them. I divided this like this. I mean, I will explain these three sessions first, and I will explain the switch level in the advanced level, where I will teach you how to draw the logic gates using MOSFETs and all. Okay, so you understand the level of abstractions. In coming slides, I will first start with gate level because it is simplest level. Then I will go with data flow level. Then I will explain behavioral level. Okay. So now we understand what are the abstraction levels, but let's start. What are the basic concepts of Verilog, right? What are the concepts like? What are how to give the comments in Verilog? How to use? What are the different types of operators that are available in Verilog? How to write the numbers in Verilog, and what are these x and z values. We'll see one by one. So how to write comments in Verilog? Very simply, you can write a comment. If you want to comment a single line, you use double backslash and then write, yes, this is a comment. Right? Why it is required? As I already told, it increases the readability of your code. Whenever you designed a very big code which is having thousands of lines and you want to specify, okay, this block needs to be optimized, right? You can specify that comment here so that later part you'll go to this module and then you can optimize. So that is the purpose of comments. A single line comment can be used by using this backslashes, two backslashes, and a multiple line. If you want to comment multiple lines, 1, 2, 3, 4, you can use backslash #. To close the comment, #backslash. Okay. Next, we'll see what are the different operators that are available in Verilog. There are three kind of operators. One is unary, and second one is binary, and third one is ternary. What does unary operator will have? It has only one operand, whereas binary will have two operands, and ternary will have three operands. Let's see examples of unary, binary, and ternary. The example of unary operator is I want A is equal to negation of C. I want not of C in A. So I can use a unary operator like this. And what is the example of binary operator? Let's say I want F is equal to A and B. Here I am using two operands and performing an AND operation and storing the result in F. This is an example of binary operators. What is the example of ternary operator? A ternary operator will have three operands like this. If A question mark B column C. So what is its functionality? If you remember, this is very similar to C language syntax, right? You are asking whether A is true or false. If A is true, true means if A is 1, then execute this statement. If A is false, then execute this statement. This is the purpose of ternary operator. It is very helpful for doing if statement, right? I mean, you are doing complete if statement in just single line. You are asking whether A is true. If A is true, then put F is equal to B, else put F is equal to C, right? You define this entire four lines of code into a single line of code. That is the purpose of these operators. Next, we'll see how to specify numbers in Verilog. In order to specify the numbers, you will write like this. You will have to specify the size of the number, and then you have to specify the base format of the number, and then you have to specify the actual number, right? So let's say I want a 2-bit binary of number 01. So how to specify in Verilog? I'll just write 2 tick. We will call this as a tick operator. 2 tick binary. I want binary format and number 01. Similarly, if I want a 16-bit 16 tick binary A B C D, right? I can define like this hexadecimal number. Similarly, there is you can even define without specifying the sizes also. Directly you can define a number like this 1 2 6 7. Whenever you don't define any base format, the Verilog will assume it as a decimal number. Okay, and you can even specify without size like this for an hexadecimal number. Let's say tick h. Sorry, this is h instead of b because it is a hexadecimal number. Tick h a b c. This is how you can specify without size also. Now let's see what is this x and z values and why they are important. We already defined different binary values like 2 tick 01, 2 tick 10 like this, right? But in some cases, you want them to be a don't cares. In that case, you can use a x. If you want a don't care like this, 2 tick 1b x, here the x will specify either it can be 0 or 1. The value of z will specify whether the node is high impedance state or not. Right? Some cases you want the circuit to stay at high impedance state. In that case, you can use this operator z. Okay. Apart from this, you can have negative numbers also. You can specify negative numbers like this. -6 tick D8. This will specify a size of 6 byte decimal number of number 8. But you cannot specify like this 6 tick D minus 8. This is illegal. You cannot specify negative sign here. You have to specify negative sign here. Okay. And there are some extra features like using the underscore to increase the readability. Let's say you want to define a hexadecimal number of 16 tick hexadecimal number in binary like this 1110110101010 like this. It is very difficult to see which bit is which. What is the bit 7 or bit 6 or bit 11 value? So you can use a hex. You can use a underscore operator like this 111 underscore 1110 underscore 0001 underscore 0010. So that you can see, okay, this is bit 0, this is bit 3, this is bit 4, and this is bit 15. Easily you can identify. The underscore operator you can use. And even you can define strings directly in Verilog like this. This is a string and all. Okay. So once we are familiar with operators and numbers, we'll go to what are the different types of data types that are available in Verilog. There is a data type called values in which you can specify the value of your register or wire like this. Let's say you have a value, there are 4 different values 0, 1, x and z, where 0 corresponds to logic low, 1 corresponds to logic high, x corresponds to the don't care condition, and h is a high impedance condition. As well as the Verilog has strengths also for these numbers, for these values, like different strengths. Like there are 8 different strengths: supply, strong, full, large, weak, medium, small, high impedance. So the driving strength is from low to high. This is strongest strength, the supply is the strongest strength, and this is the weakest one. So what is the use of these strengths? Let's suppose you have an AND gate, two AND gates that is merging two signals and giving to a single input. In this case, if one of the input is having strength of supply or strength of strong, and one of the input is having strength of weak, what will happen? This node will be driven by this value. Let's say that the value here is 1 and the value here is 0. It will driven to the highest strength value. Here in this case, the strong is the highest strength compared to weak. As you can see, the strong is here and weak is here. So the value will be 1 instead of 0. Why do we require these things? While you are designing any circuits using MOSFETs, you might have observed to give the strength of the currents, we will change the W by Ls of the MOSFETs, right? That kind of functionality can be implemented by using strengths here. Let's say you have this one is having low strength and this one is having high strength. Let's say this W is very high and this W is very low. Then the signal that is traveling through this will be affected on this line. The same kind of functionality can be obtained here by using these different value strengths like strong, weak, full, medium and all. So that is about values. And now let's see what is a net and what is a register. The net and register are two most important data types that are available in Verilog. A net is represented by using a keyword called wire. So often in this course, we will use net and wire as interchangeable words. The net is used to represent connection between hardware elements. What I meant is, if you have any circuit like this, the net or wire is this connection. It represents connection between hardware elements. So the value of net is always driven by some output like this. In this case, the value here is equals to, let's say this node is y, then y is equals to a dot b whole bar. It is always driven. As you can see, the value is always assumed based on the input patterns here. By default, the value of net is a Z value. If you don't specify anything, the value of net is always Z. And by default, the wire is a 1-bit value. Okay. So let's see the examples how to define wire in Verilog. You can define wire like this: WIRE A, comma B, comma C. So it means A, B, C are three different wires. Each is having 1-bit value. And wire D is equals to 1 tick binary 1. So here I am defining the wire D as well as I am assigning the value of binary 1 to wire D. If you don't assign any value, by default these A, B, C are in high impedance state. Right? Now let's see what is a register. A register represents a data storage element which stores the data until the next data arrives. So what I mean is, in the case of net, the value is always driven based on the inputs, right? As I have shown in previous slide. But in the case of register, the value once you assign will be changed when you assign next time. When the next data is coming, then only the value here will change. Until that time, the value of the register will retain. So how to represent a register? By using a keyword called reg. So the default value of a register is X, either 0 or 1, which is a don't care condition. So let's see an example how to define a register and assign values to a register. I am defining a register of variable reset. Initial means I am initializing the process. The begin and end are similar to curly brackets that we use in C language. If your number of statements are only single statement, then you don't need to use begin and end. If the number of statements inside the initial are multiple, then you will use begin and end. Here I am putting a value of 0, binary 0 into register. After 50 nanoseconds delay, I am putting value of 1 on this variable register. So during this period, the value of 0 retains its value. The value of 0 is stored in variable called reset. Okay. Don't confuse this register with hardware registers, like we have designed a hardware register using D flip-flops, right? So that is a different story. That is a register which is a hardware element that used to store the data. But this is a data type which is a variable that can be used to store some data, and its purpose is it will retain the data until the next data arrives. That is the main difference between a net and register. Okay. Now let's see what is a vector. The wire and register, whatever the net or wire or register, can be a single bit value or it can be a multi-bit value. The multi-bit values can be either one dimensional, which is a vector, or two dimensional, or any number of dimensional, which is an array. So if width is not specified, then by default the wire and registers are taken as a one bit value. If you want to specify width like this, wire 15 down to 0, I am calling this operator as down to because it is easy to remember that you are going from 15 to 0, 15 down to 0 data. So what I am defining here is the data is a vector of length 16 bit. If you don't define the size, then the data is a single bit vector, single bit wire. Okay. So the vectors can be declared in two formats. One is high number to low number, or other way, low number to high number. Usually we will take high number to low number because in Verilog always the left number is the MSB bit. So if you define a wire like this, wire of 7 down to 0, this means the 7 is the MSB and 0 is the LSB. In conventional way also 0 is less than 7. So it is better to define high number down to low number, because if you define something like this wire of 0 down to 15, then in this case the MSB is 0 and LSB is 15, but it is little bit confusing because 0 is the least number and 15 is the highest number, but we are assigning MSB to 0. So it is always preferable to use high number to low number, and always write like this wire, while you are writing just count like this wire 7 down to 0, which means a 8 bit vector of a wire. Okay. So that is how you can define a wires, and you can even define registers also. In this case, as I told, this is a low number to high number case. It is a 32 bit address register which is having MSB of 0. Okay. So now let's see how to do vector part select. Since normal wire and register as single bit values, you can directly assign to them as I showed in the previous slide, like register count is equal to 1 tick binary 0. You can directly assign because it is a single bit value. But how to assign for a multi-bit vector kind of thing? So let's see how to assign. You can assign complete vector in the initialization stage, or you can assign part of it also. So the vector part select will define how to assign part of the vector. So how to assign a part vector? Like this. If you have a data bus of 16 bit and you want to assign to 7th bit, then you can directly call data of 7 is equal to 1 tick binary 0. This way you can assign the 7th bit of the data to binary 0. Similarly, you can call multiple values also like this data of 5 down to 0. So by this, what do you mean is the first 6 bits of data are going to be called. Okay. But you cannot call in reverse order. Here it you have defined from low number to high number, and you want to call like this address of 2 down to 0. You cannot call. This is an illegal calling because here you have defined from low to high and here you are calling from high to low. So always remember, the way you define, you need to call the same way. Okay. That is vector part select. The variable part select will be very useful if you want to select various vectors or various parts of vectors in a very big vector like this. So let's see an example how to use this variable path select. There are two ways to define the variable path select. One way is you define starting value and plus and how much width you want. And the other way is you define the starting value minus how much width you want. So this is called part select increments from starting value, part select increment from starting value, and this is called part select decrement from starting value. So we will see how we can use those two. So let's take an example like this. I have a register of 256 bit and I have a register of again 256 bit. So you see the difference between the difference between these two registers is this is high number to low number, which we call it as a little Indian notation. Little Indian notation. Because the low number is ending at the right hand side. So it is a little Indian notation. In this case, this is big Indian notation because the big number, high number is ending at the right hand side. So as I explained, you cannot have you cannot define little endian and high end while retrieving value from little endian. You have to follow little endian sequence only. While retrieving value from big endian, you have to follow the sequence of big endian only. So let's take an example how to select from this register. Let's take an example. If I want to select a part of this, various parts, not a single part. We have already seen how to select a single part, right? You can directly define like this: my byte is equals to data 1 of 7 down to 0, let's say. This is one way of selecting. But let's say you want to select various parts where you can use a for loop just like in the case of C language. So let's see how to do that. So first I'm doing manually. I'm selecting different bytes from this data 1. So how to do that? Byte 1 is equals to data 1 of, since it is a little Indian kind of thing, so I have to specify bigger number here, 31 minus 8. So what does this define is I am selecting a data from 31 to 24. 31 minus 8 means it is defining a width of 8 bit. Okay. Similarly, I can select one more byte of data from this data 1 like this: 24 plus 8. So what does this mean? It is selecting a data of 24, 31 down to 24, right? Since it is a little Indian kind of notation. Similarly, if you want to select data from this big Indian notation, you can write like this: my byte 3 is equals to data 2 of 31 minus down to 8. Okay. So in general, if you want to select any data, the syntax is like this: start value plus down to width and start value minus down to width, right? This you can do manually, but if you want to automate this thing, if you want to use a for loop, because writing this will take so many lines of code, right? If you want to do it in a single line of code, you can use a for loop. By using for loop, you can get all these bytes. Let me show how to do that. Instead of writing individual bytes, instead of getting individual bytes, I will write a for loop and I will get all the various bytes that are available inside the data bus, which is a 256 bit data bus. So how to do that? First, I will define my for loop. For I am defining a variable j 0 to j less than or equal to 31 j plus plus. Right? Now I am taking byte data is equals to from data 1. I am calling from j multiplied by 8 plus 8. So what it does is when j is equals to 0, it will take data from 0 to 7th bit, and when j is equals to 1, it will take data from 8 to 15th bit. Similarly, when j is equal to 2, it will take data from 16 to 23rd bit. Like by this way, you can have data from this big data register. You can have multiple small datas, whatever you want, right? Next, we'll see different data types like integer, real, time, and parameter, and what are their uses. The integer is a general purpose register. You can use register also, but the advantage of integer is integer will have a width of your mission, the mission that you are running. If your mission is a 32-bit mission, then it will take a width of 32-bit, and if your mission is a 64-bit mission, then it will take a width of 64-bit. So that is the size of the integer. And how to initialize the integer? Let's take an example. You have to use a keyword called integer, and I am taking a variable called count. So my count is a integer data type, and I am initializing the value of count initial. The initial statement will tell me beginning of the program I am initializing this value. So initial, since I am using only one line of code, I am not writing the begin and end. You remember, right? If you want to write multiple lines, you have to write begin and end. Here I am writing only single line, so I am directly writing my count is equals to 1 tick binary 0. Or you can do again initial. Let's take I want to define a negative number. I can directly write count is equals to minus 65. Like this. You can assign any positive or negative numbers with a size of 32-bit or 62-bit in the case of integer. And what is the data type of real? A real will store the real numbers. Any numbers like this 1.525 or 3.14, which is a pi, like this. It can use to store values in both scientific notation and decimal notation. So how to do that? If you want to use the real numbers, you can use a data type called reg. Okay. So I'm using a data type of not reg. I'm using a data type of real. Okay. Real, I'm putting a value of pi. Let's say pi is my variable. Okay. How to initialize it? Again, initial begin. I'm writing multiple lines of code. So begin, I can write pi is equals to 3.14 initially, or I can write pi is equals to 3e1, which means it is a value of 3, right? This is a scientific notation and this is a normal decimal notation, decimal point notation. So every statement in Verilog should end with semicolon, right? Except these keywords like initial and begin. So I am ending these statements with semicolon and I am closing the begin with n. So this is how you can write a variable of pi with different values like this 3.14 and 3.1, 3.1 like this. So you need to remember one thing. If you are calling this value into some other value like this integer, let's say I want to call this into the integer j, where j is equals to pi, then what it does is it will truncate the value to the nearest possible value. In this case, the 3.14 will be truncated to 3. Okay, whenever you are converting from real number to integer, it will truncate the value and it will round off the value to its nearest value. So that is integer and real. Now we'll see what is a what is a data type called time. The time data type is used to store the simulation time. For this, you will require a system function called $time. So how to use the time data variable? How to use the time data type? You just use the keyword called time I'm using a keyword called time, and I'm taking a variable called my sim time. This is my simulation time, close with semicolon. Now I am initializing with my sim time is equal to $time. This is how you get the simulation time.